Okay, we are going to start with a new topic, which is like approximate the solution of differential equations. So here we will consider the two classes. The first class will be we will work with initial value problems. So as the name suggests, and I hope you are also aware that what do you mean by initial value problem, which is defined as y dash is equals to f of x comma y of x with, let's say, x belongs to closed interval AB. And for the uniqueness of the solution, we have defined the initial conditions y at x naught equals to y naught. So y naught is given at x naught value, y value, only this information is known to us, and this the above differential equation is there. Okay, and y dash is stands for dy by dx. So we are going to look at the approximation of the solution of this problem. Okay, so this problem we are name it with 1. Okay, which involves only ordinary derivative. We are not going to work with here partial derivatives. Okay, so we are only going to work with the first order ordinary differential equation for this one class. Another problem what we are going to look for is boundary value problems where the order of the differential equation is of second order, and then with the specific conditions. So the conditions will be most of the time specifically specified at two endpoints. Okay, like x naught and x1, or let the point A and B, what are the values of y? Or maybe they will be in the term of one is y at x naught, and another is in the term of y dash at x naught. Okay, or maybe mix of them. Okay, so there are various ways to define the boundary conditions for boundary value problems. So there we are going to look for the solutions by using the what we have learned during numerical differentiation. Okay, means we are going to approximate the derivatives by the finite differences. Okay, so we have learned some forward difference operator, a central difference operator during interpolation techniques. So we are going to utilize those tools to approximate boundary value problem, which will be turned out in the form of solving a system of linear equations, and there you will use the iterative methods and so on. That we will look at in the second case. So here we are going to first look for initial value problem. Okay, so for if as you are aware, means you may have learned during your calculus class as well, when this initial value problem, which is also in short is given as IVP. Okay, when this solution will have unique solution. Okay, so the very simple geometry where we can look at is a rectangle which contains the point you can say x naught and y naught. Okay, so initial point is x naught equals to a, so this x naught is also, it can be replaced by a. Okay, so we are going to look for the solution in some rectangle, which we are going to denote it by d. Okay, and where the point a comma y at a, or a is x naught, okay, is an interior point of the d. So we are going to specify some conditions on the function f, so that this problem will have a unique solution. Not that we are taking a comma y of a, or x naught comma y naught, in other words, x naught comma y naught as an interior point of this D, not as a boundary point. Okay, and then you will have learned the way to approximate the solution, Picard's approximations, and so on. The name of the theorem is Picard's theorem, which gives the guarantee of the existence and uniqueness of this problem. Okay, so I will specify the assumptions on the right hand side function f, which will guarantee that the solution exists and it will be unique. Okay, so the result is as follows. So we have been given with the initial value problem. We have been given with the initial value problem, which is given by dy by dx. This which we are going to denote it by y dash. That is equals to f of x comma y. Y is a function which is depending on x. Okay, with the initial condition, let's say y at a is equals to y naught. Okay, so we want to look for the, so we are looking for the result. So here is the result, which gives the guarantee that the solution exists and it is going to be unique, because it also proves the well-definedness of your problem. So what it says is, let this right hand side, because we can only talk about this right hand side function. Okay, so let f of x comma y be continuous, let f of x y be continuous on rectangle D. So D is the rectangle, if you have, is that it's a pair of points x comma y, such that mod of x minus x naught is less than equals to a, and mod of y minus y naught is less than equals to b. That also is a very specific form of the rectangle. Let f be is continuous on this D, and f satisfies the following condition, and mod of f of x comma y1 minus f of x comma y2 is less than equals to k time mod of y1 minus y2. So if you refer this is nothing but the Lipschitz condition. So f satisfies Lipschitz condition with respect to the second variable. Okay, so there exists some constant k such that this condition satisfied for this variable with respect to second variable. So these x comma y1 and x comma y2 are the pairs inside D. So for x comma y1 and x comma y2 belongs to D. If these two conditions are satisfied, so f be continuous and this f satisfies this Lipschitz condition. So this condition is known as Lipschitz condition. Lipschitz condition. Then 1, this equation 1, then 1 has a unique solution. Unique solution. Means solution exists and it is unique. Okay, so let's take one example. So let us consider this condition equation y dash equals to y, with y at 0 is equals to 1, which you can solve by using variable separable method. You can use dy by dx equals to y, and dy is equals to dy by y equals to dx, and you can integrate and you can find that arbitrary constant, and you can show that the solution will be e to the power x. Yx is equals to e to the power x, where x belongs to 0 to b. Okay, Now look at a function right side. So if you look at the function f of x comma y is equals to y. This is a polynomial in y. So this is remain continuous everywhere. So this will be continuous on R2. On xy plane, it will be remain continuous. The secondly, the next condition that mod of f x comma y1 minus f of x comma y2, if you look at, that is going to be mod of y1 minus y2. So it satisfies the Lipschitz condition with k equals to 1. So both the condition of the above result is true. So the above result gives the guarantee that this has a unique solution. Okay, so without looking at this, what is the solution, you can easily give the guarantee that there exists a unique solution. Okay, now moreover, if you look at this condition, okay, look at the condition, look at this condition here. So this Lipschitz condition, this is a weaker assumption of something. Okay, so if you take y2 is equals to y1 plus h. Okay, let's take y2 and y1. So let's take y1 is less than y2 or y1 is greater than y2. So we can arrange that order that yn is less than y2 and y2 is y1 plus h. So this condition will gives you what, or tends to what is, so if you look at this condition, so let y2 is equals to y1 plus h. Okay, then this the Lipschitz condition mod of f of x comma y1 minus f of x comma y2, that is y1 plus h, is less than equals to k time mod of y1 minus y2, that is going to be h, mod of h. So this will turns out to be, so h is any greater than 0, strictly greater than 0 number. So mod of f of x comma y1 minus f of x comma y1 plus h divided by h, the complete magnitude is going to be less than equals to k. Now if you apply limit h tends to 0, okay, so if you apply limit h tends to 0, the left side is nothing but the partial derivative of f with respect to y at y. Okay, so limiting value of h, limit h tends to 0, it will be fy at y1, right? So but you know that differentiability, this assumes the differentiability of the function, but previous one was not referring the differentiability that you can easily verify. So this implies if exists. Okay, so that's okay. So let me go to the next slide. So this certainly implies dou f by dou y mod is less than equals to k on d, okay, whenever it exists. So this has a very strong meaning, whenever it exists. So it may or may not exist. So for example, look at the function. Okay, so let's look at the function. Your right hand side is f of x comma y is equals to, let's take mod y. And you are taking the rectangle D containing 0. Okay, rectangle D containing 0. This modulus function, you know, differentiable everywhere except at 0. Okay, so dou f by dou y at 0 does not exist, so it will not remain bounded on the interval D. So this is what is happening. But if you look at the mod of f of x comma y1 minus f of x comma y2, that is going to be mod of mod y1 minus mod y2, which is certainly less than equals to mod of y1 minus y2. So the f satisfies the Lipschitz condition, whereas dou f by dou y does not exist. not exist in any rectangle D containing 0. Containing 0. So if you exclude 0, that's a different thing. Containing 0, 0, 0, 0. Okay, so the ellipsis condition is weaker assumption than the derivative. Okay, so ellipsis condition may or may not imply the differentiability, but differentiability certainly implies. So from here you can go back, you can traverse back and show that whenever it exists and it is bounded, then you can show that the ellipsis condition satisfied. That by using the mean value theorem you can say. Okay, that by using the mean value theorem. Okay, right. So this is the weaker assumption what we have. And for the right hand side, if you choose mod y, you can show that there dou f by dou y does not exist at origin, near origin. So then you know, but ellipsis condition satisfied, so solution exists and it is unique. Okay, right. Okay, now what is our main goal? Main goal is to approximate the solution for the IVP y dash equals to f of x comma y with x belongs to say closed interval a to b and y at a is equals to y naught. We want to approximate the solution, okay, at points, you can say a plus h, a plus 2h, a plus 3h, and so on. Okay, or midpoint of this interval, or at the point B, you can say. Okay, now, so there are various ways to approximate this solution, the solution of this problem. Okay, so one of the ways is write down the Taylor's approximation for a given function y about the point x naught. So that's a one way. So let's so if I go with the Taylor's approximation, so that's the one way. So Taylor's approximation implies the following. So I'm just mentioning implies the following. So what is here is, so you are going to approximate y about the point x naught. So certainly it requires the differentiability of the function f. Okay, so let's assume that it's it's sufficiently differentiable as many times as we require. Okay, so once it is there, or let's say second derivative is exists, or it is two time differentiable. Okay, so suppose this is there, that then it can be written as y at x naught, Taylor's approximation, plus x minus x naught times y dash at x naught, plus x minus x naught whole square by 2 factorial, then y second derivative at some point c, which lies between x and x naught. Okay, so this is the Taylor's approximation, and so we know what is y at x naught, that is y naught. What is y dash at x naught? So x minus x naught. Y dash, so y dash is f of xy at x naught is f at x naught comma y at x naught, that is y naught, plus this error term. So that is going to be x minus x naught square by 2 by second derivative cx. Right, now see, we can truncate this series and we can assume that this is the approximation for any value of y at x. This will give you the approximation, and this will be the truncation error, you can say, and discretization error, or in other words. Okay, now before going further, we have simply assumed that y is second time differentiable, two time differentiable, or three time differentiable. If we require Taylor's approximation for means like or higher powers if we go, then we require differentiability of function y. How do we judge? Because y is not unknown function. We don't know what is the value of y. Okay, so or what is the expression for y. So what we will do? So what we have in our hand is we have the right hand side f of x comma y. So we know that y dash is equals to f of x y means a one time it is at least differentiable. So that we know. For further differentiability, it totally depends on the differentiability of the function f. Okay, so now, so if we want this is going to be differentiable, means we want y double dash to be exist. So let's calculate y double dash. So given y dash is equals to f of x comma y. Now, what is y double dash? That is nothing but d by dx of y dash. Total derivative. Apply the implicit differentiation rule. That is going to be f partial derivative with respect to x, dx by dx is 1, plus f partial derivative with respect to y, time dy by dx, that is y dash. Okay, now note that to have second time differentiability, what is required here is if we assume that partial derivatives, first order partial derivative exists and continuous. So then second derivative exists because y dash is already available. So you can replace it by fx plus fy time f, and which is evaluated at x comma y, the point x comma y. Okay, now if you want third time differentiability, okay, so if you want 3 time differentiability means you are going to find y third derivative. Okay, so this implies this. Now this implies y third derivative, that is going to be d by dx of this one. So we are using the abuse notation, so we are not carrying forward this x comma y. Wherever they are occurring, we are assuming that they are evaluated at the point x comma y. Okay, now apply the again implicit differentiation rule and chain rule and product rule here. Okay, so what you will get is the first term is fx derivative with respect to x, then dx by dx is 1, plus fx, then derivative with respect to y partially. Okay, and then you have dy by dx, that is y dash. Okay, so that is going to be here in notation form. This is going to be fyx. Okay, so because dou square f by dou y dou x. Okay, right. So that's for the second term. For this is differentiation of the first term. Now the second term we are going to use the product rule. So the first term is derivative is f y partial derivative with respect to x, so x y time dx by dx is 1 plus f y y time y dash second function as it is plus first function fx plus fy dot f time the derivative of this is going to be here. We are differentiating now fy dot f, right? So f into the derivative of fy plus fy into derivative of f, total derivative fx plus fy dot y dash. Now open it up. So what you will get is fxx plus. Now also assume that mixed derivative theorem, which gives the guarantee that fyx and fxy both are the same thing. Okay, so it doesn't matter in which order you differentiate. So apply the mixed derivative theorem, which assumes the continuity of second order till second order partial derivatives. So if the second order partial derivatives are continuous, okay, that can be addressed by looking at the expression of function f. Okay, there is means it is not difficult to decide that whether function is two-type differentiable and second derivative is continuous or not. So many times it can be directly observed. Okay, so suppose mixed derivative theorem is applicable so that fyx and fxy both are same. Okay, then so you have y dash is f. So I'm going to replace here fy dash by f. So you have this is 2 times fxy dot f. So this term is over now, this term and this term. Okay, now then you have plus fyy dot, this is f into f, so fyy times f square, right, plus fy fx plus y dash is f times fy whole square. So for having the still third order derivative, means y should be 3 times differentiable, you require the continuity of the second order partial derivatives, including the first order of the first order partial derivative, and so on. Okay, so once you are imposing the condition that y is twice differentiable or three times differentiable, so if you observe from the expression for the f that it is going to be differentiable as many times you require, so you try to go for higher order schemes. Okay, so now let's come back to our main problem now. So we are what we have assumed that, so Taylor's approximation implies the following. So as here we have assumed that y second derivative does exist. Now we are saying that, so what will be the approximation now? So from there, what will be the approximation is y at x is, so approximated is equals to by, or you can say approximated by y at x naught plus x minus x naught times f at x comma x naught comma y naught. Y dash at x naught can be replaced by y naught. We can replace y at x naught by y naught as well. Okay, that we can use as a notation. And what we are what we have, the error is equals to x minus x naught square by 2 times second derivative c. Some c point is lies between x and x naught. Okay, so this is when we are assuming that we have assumed that y is 2 times differentiable. So 2 times differentiable. Now you can check from the Taylor's approximation theorem or Taylor's theorem that it is giving you the good approximation in the neighborhood of the point x naught. Okay, so if you look for the closer point, then the error will be small. So look at here. So if you go, suppose x naught to x1, so you let's say you are going to find that y at x1. Okay, then the x1 minus x naught. So that x1 minus x naught whole square will be present in the error term. Okay, so if x1 is very close to x naught, the error will also be small. Okay, so but our agenda is not to find the values of at x1. Our agenda is to go to the for finding the value of y at b. So what we will do in this case, what we are going to do is we are having the interval a to b. So like we have done previously, so we are going to define partition with equispaced points x1, x2, and so on, xn minus 1. And so then you are going to take the approximation at x1, then use this approximation to get the approximation at y at x2, then use this approximated value to get the y at x3, and so on. And then you will find the value of y at b, so that the error will be less. Now, but what it suggests is you should choose x1 as closer to x1 closer to x0. Similarly, this step size to be sufficiently small. Okay, but what is happening here more? The things are happening is from here to here. Okay, there is not much error between y at x1 and y at x0, because y at x0 is exact value. Okay, so y at x1 will have some round of error. Then if you go go to y at x2, so that it will also add it up here. Then if you go from y at x2 to y at x3, that will also round of error is also added up here, and so on. So at the end, you will end up with enormous, like a round of error will be very large. Okay, so what? So it is not suggestible that you will choose a very small intervals, okay, to reach this peak. Okay, so one needs to be careful while choosing the right scheme for the considered problem. Okay, so definitely you requires the order of convergence then higher, means like sufficiently, means h should be not very small and it should not be behave like this. Okay, but so similarly, if you add it up here, so what you will get? So here, suppose if I use this, okay, for getting the x1, so I'm here now. So the above formula suggests you y at x1 can be obtained by y at x0 plus x1 minus x0 time y dash at x0, that is f at x0 comma y at x0. Now we are going to use some notations as follows. So y at xn plus or xn, we are going to use as the exact value. Okay, exact value. And y with suffix n, we are going to say is approximate value. Okay, approximated value at x equals to xn, an exact value at x equals to xn. Okay, so from here using with y at x1, so this will give you, so you have this is y1 approximated by y0. So approximation now y1 equals to y0 plus h time f at x0 comma y at x0, that is y0. Now y2 is going to be given by y1 plus h time f of x1 comma y1, and so on. So that yn plus 1 is going to give you that yn plus h time f of xn comma yn. So here you have you are reaching the point B in n steps, you can say. Okay, x1, x2, and so on xn. Okay, so this the formula what we have developed is called Euler's method. Okay, so this method, the formula what we have developed is called as Euler's method. Okay, right. So what is h is? What is h is? H is defined here. So h value is xi plus 1 minus xi is equals to h. Okay, and that is equals to b minus a by n. Okay, that is going to be h. Right now, let's write the things what had happened now so far, and or you can say let's summarize the things now. Okay, so what we have got is Euler's method for approximating the solution for the given IVP. Okay, so what is there is y dash. So given IVP is y dash equals to f of x comma y, where x belongs to A to B. And the initial condition is y at x naught, that is nothing but y at A, and that is equals to, we are calling it y naught. And then we want to find the value of y at point B. Okay, so how do we reach this B? We are going to create the partition A equals to x naught, less than x1, less than x2, less than, and so on, less than xn is equals to B, and where h is equals to, you can say B minus A by n. And xi's are nothing but A plus IH. I is equals to 0, 1, 2, and so on, n. Then what you have is formula for Euler's method is, I'm just going to state here, is yn plus 1 is equals to yn, or you can, instead of n, you can use k. Okay, yk plus 1 is equals to yk plus h time f of xk comma yk, with n k equals to 0, 1, 2, 3, and so on. So you can reach with k with a y at value b by choosing k equals to n minus 1. So n minus 1, if you choose n minus 1 plus 1 is n, and at xn value is b. So you can so what you can do with this data now? So you can also, you will be available with the data now. So which is, so you can say approximated data now. So the corresponding data points and corresponding values of y. So x naught, x1, and so on, xn, and you have corresponding approximated values y naught, y1, and so on, that is yn. So what you can do, you can actually now interpolate it to find the shape of the curve. Okay, and you can use spline interpolation, you can use Hermite interpolation, other interpolating technique for getting the curve y. Okay, right. So this tends to Euler's method, with which we have obtained by using the Taylor's theorem. Okay, which we have obtained by using the Taylor's theorem, and we have truncated after first a second term. Okay, so which we have truncated after second term. Okay, right. Now let's talk about the error now. Okay, in Euler's method, error in Euler's method we are going to talk. So what we have is exact value y at xn plus 1. Exact value at xn plus 1 is y at xn plus h time f of xn comma y at xn plus h square by 2 time y second derivative at some c, and which is going to be depend on between the points you have. This is yh is here is because xn and h, xn and xn plus 1 are equispaced with the space. So here h is nothing but xn plus 1 minus xn. Here you are writing that Taylor series about the point xn. So you can write xn plus 1 as xn plus h, and you can obtain this. So this term is referred with y dash at xn, and which we are going to replace by the equation y dash equals to f of xy. Okay, so and this is y double dash at cn, that is going to be error term. So here if I want to specify xn plus 1 minus xn is equals to h, they are equispaced. So this is the exact value where this will be the error term. Okay, right. Now in Euler's method, yn plus 1 is yn plus h time f at xn comma yn. Now, if you define error at nth step is going to be exact value minus approximate value, then we can have the following. So en plus 1 is equals to so en plus 1 is y at xn plus 1 minus y at n plus 1 that you can have here. Okay, and then you have this is y at xn minus y at n, that is going to be en plus h time f of xn comma yxn minus h time f of xn comma yn. So this is plus h time f of xn comma y at xn minus f at xn comma yn, and this term, this is the term which we can, so plus h square by 2 y second derivative at some cn which is lies between xn and xn plus 1. Okay, so this is the total error in Euler's method. Okay, this is the total error in the Euler's method, and next is this error. Okay, this error, the last term in the sum is called as local discretization error or discretization error. Okay, discretization error. So this thing, so we can obtain total error in Euler's method, but not in all other methods we can obtain. So we are going to worry most of the time about the discretization error. So this is local because it's from the step xn to xn plus. This is called discretization error. This is here local discretization. Okay. Now, what we are going to do now? So can we do something about it? This term. Okay. So let's look at it here specifically. Now we know that. So we are assuming some assumptions here now on the function f. So what assumption we want is now f is satisfying the Lipschitz continuity, or not only Lipschitz continuity or Lipschitz condition. We assume that the dou f by dou y is bounded. Okay, or you can say partial derivative exists with respect to y and it is bounded. So how it will help us? Okay, so now, so what we have is from the previous step is en plus 1 is equals to en plus h time f of xn comma y at xn minus f at xn comma yn plus h square by 2 y second derivative at cn, where cn lies between xn and xn plus 1. Okay, now assume that the first order partial derivative exists with respect to y. F is differentiable with respect to the second variable. So see, keeping the first variable fixed. So keeping the first variable fixed. So this is a function of y. Okay, and it is differentiable with respect to y and it is continuous. So you can apply the mean value theorem. So mean value theorem in differential calculus, what it implies, there exists some yn bar, okay, some yn bar in y at xn, between y at xn and yn. Okay, in this interval yn between y at xn and yn, such that f of xn comma y at xn minus f at xn comma yn can be approximated by dou f by dou y at xn comma yn bar, here divided by y at xn minus yn. Now, not that this denominator y at xn minus yn is nothing but en. So, by using the mean value theorem now, what it will imply? So, we have assumed here that f is differentiable with respect to second variable. Okay, or partial derivative of f with respect to y exists and continues. Okay, that we have assumed here. Okay. So, with this, we have this en plus 1 is equals to, so this is en plus h time fy xn comma yn bar time this, so that is en, so that is type en plus the third term h square by 2 f y second derivative at cn. Now, what as already mentioned, because we are looking for the scheme which is going to converge to the root, okay, or in other words, which is going to give you the better approximation at the end. Okay, so we require definitely that error is going to remain bounded. It should not blow up. Okay, so what we require is we are going to assume that this dou f by dou y is remain bounded. Okay, let's say assume that this is remain bounded and assume that the second derivative is also bounded. Okay, so if we have, so because see, we can evaluate second derivative by using the definition of f. Similarly, we can, if it is required third derivative, then you can again use f. You have to differentiate 3 times partially and so on. That complicated some expression will come, but definitely you can get the expression. Okay, so now what we are going to assume is, so for looking at the boundedness of the error, so we are going to assume that, let's say we are assuming that mod of fy, so the xy at any point xy inside D is less than equals to k on D. Okay, xy belonging to D, and let's say mod y double dash at x is less than equals to some m for x belongs to closed interval E. So if we have this assumption, then mod of en plus 1 is going to be, so go back and apply the triangle inequality mod, then apply the triangle inequality mod en plus h is greater than 0 number, h mod fy mod en plus h square by 2 times mod of this. So apply the triangle inequality, and then what you are going to have is less than equals to. So the first is mod en plus 1 plus h time mod of fy is less than equals to L. So mod en plus h time L time mod en plus h square by 2 time m. So what is this? Is nothing but the 1 plus h time L time mod en plus h square by 2m. Now, so this is the relation. So this relation, if you use continuously, okay, so if you use continuously this relation, so this will implies, so if I use mod en, it replace n by n minus 1 both sides, so you will utilize the relation. So this remain fixed. So you use this, so what you will get is this is further less than equals to 1 plus h time L. Now mod en is less than equals to 1 plus hl time mod of en minus 1 plus h square by 2 time m plus h square by 2 time m. So if you simplify this expression, that is going to be 1 plus h time L whole square time mod of en minus 1 plus, Now h square by 2m is remain common. So h square m by 2 time 1 plus HL. Now, if you again use it, so this is going to be further less than equals to 1 plus HL cube mod of En minus 2 plus h square m by 2 time 1 plus HL plus 1 plus HL whole square, and so on. So keep on using this recurrence relation. What you are going to get is, so this implies mod of En plus 1 is going to be less than equals to, if you follow it up, that's going to be 1 plus HL to the power n plus 1 time mod of E0. So look at back. So if you look at the sum of this power here is 1, n is n plus 1. Sum of these suffix and power. So the second here, if you, so 2, n minus 1 plus 2 is n plus 1. N minus 2 plus 3 is n plus 1, and so on. So what will be is till mod E0 plus the second term is h square m by 2 time 1 plus h time L plus, so previously you were having here cube, so you are ending with the square, right? We are having 2, we are ending with the power 1. So you can follow the pattern now. So this is going to be till plus 1 plus h time L to the power n. Okay, right? Okay. So now what will happen now? Now look at this. So what is E0? E0 is y at x0 minus y0. So, but that is 0 because at starting initially there is no error. So this term vanishes. So this term does vanish. Okay, so this will not contribute anything because mod of E0 is 0. Okay, so since this is there, so therefore what you will have is mod of En plus 1 is going to be less than equals to h square m by 2. Now, so look at this. This is 1 plus x square and so on plus x to the power n. So what is going to be? This is going to be, if you going to be 1 plus HL to the power n plus 1 minus 1 divided by 1 plus HL minus 1. Right? So this 1 plus 1 minus 1 get cancelled, right? 1 plus x to the power n is nothing but the x to the power n plus 1 minus 1 divided by x minus 1. So that you can verify now. Now, what is there is now is, this is going to be less than equals to, so this is equals to, now one h will get cancelled, so we will have is h time m by 2l time 1 plus h time l to the power n plus 1 minus 1. Okay, so from here we can certainly show that this is going to be mod En is less than equals to hm by 2l time, here n will be replaced. Okay, right. Now next here, so this implies mod of En plus 1 is less than equals to h m by 2l time 1 plus HL to the power n plus 1 minus 1. Okay, this is what we obtained just. Now, note that whenever x is greater than 0, okay, then we will have always e to the power x is greater than 1 by x, 1 plus x, right? Greater than equals to 1 plus x. Okay, so this will imply certainly e to the power nx is going to be greater than equals to 1 plus x to the power n. Okay, so we are going to use this here. Okay, so what it says is this 1 plus h to h times l to the power n plus 1. Okay, so that we are going to use now. So this will implies, so instead of n plus 1, now we can work with n. So instead of, you can replace it by this here. So this implies mod of en is less than equals to hm by 2l time. Now 1 plus hl to the power n is less than equals to e to the power m h l minus 1. Now look at this n time h. What is n time h? hm by 2l. What is it? This is nothing but xn minus x naught time l minus 1. So if you fix xn, this mod en is bounded. If you kept if xn is kept fixed, then mod of en is less than equals to some c time h. Okay, so this will have some finite value. Okay, this will have some so this difference with constant m by 2l, this all this will come into this constant c and h. So in the Euler's method, okay, if you proceed with n steps, so you have lost the 1 power of h, because you have started with h square by 2 if you previously look at. Okay, but once you subdivide the interval into n equal sub intervals, and if you totaling up all the errors down, okay, then you have also in the similar fashion as you have seen during the numerical integration as well, that you have lost 1 power of h. So this is going to be means like this implies en is, or mod of en is approximately of h, because when n goes large, it's going to towards the equality. Okay, so the error is behaves like of h. So order of convergence of Euler's method is 1. Now suppose we want the desired accuracy is suppose 10 to the power minus 6. Okay, so if you bound it by less than 10 to the power minus 6, so then you think how much small h is required. Okay, right. So definitely you require the improvised method one. Okay, which has order of convergence or higher order of convergence. Okay, so again you can now go back and modify your Taylor's approximation. Okay, by using the Taylor's method, which requires a derivative, and you can develop the Taylor's method of order k. Okay, and then you can work with the function evaluation, its derivative evaluation, and substitute the value and approximate the function value. Okay, a non-function value. That's the very first way. Other ways, we are going to look at some other means except this derivatives. Can we get rid of derivative? So suppose I have the function given. I have been given with the function, and I want a method which only require the function evaluation. It does. We don't want to evaluate the derivative. We don't want to evaluate first order derivative, second order derivative. We don't want to get into it, and that should be, and also that should be that should have the higher order convergence. So that's our next call, which we are going to do in the next session. Okay, so that we are going to do in the next session. So here we are closing the session 2 for today.